In video 39 of the Foundations of Computational Economics course, we will look at the first-order conditions for dynamic problems, derive the Euler equation, and talk about the time iterations as a solution method for the infinite horizon problems. So we have a maximization problem in the Bellman equation, and thus we can write the first-order conditions for this maximization problem, well, provided that the choice variables are continuous, of course. Is there any use for the first-order conditions? Well, of course there is. First, we know that the first-order conditions must be satisfied by the optimal policy, the policy function that is part of the solution of the dynamic model. And so that means that we can use the first-order conditions to find that solution, to find the optimal policy. And then we can formulate solution methods based on the first-order conditions. And indeed, in video 37, in the overview of all of the solution methods, we've mentioned backwards induction with equation solving instead of optimization for the finite horizon problems, or time iterations, which is the solution method for the infinite horizon problems that is centered around the first-order conditions. But moreover, imagine that we solved the model with some other solver, with some other numerical procedure. The first-order conditions must be satisfied irrespective of the way that the problem is solved. So we can formulate the quality checks for the other solutions based on the first-order conditions. So if the model is solved by some other method, then we can still use first-order conditions to try to say whether it was solved accurately. And things like early residuals that we will look at in this video and implement in the next video is a good and widely used approach to accuracy check of the solutions. Now, a flat consumption path must be simulated with certain restrictions on parameters from the consumption savings model. This is what's known among some people as Keen's test, named after Professor Michael Keen, currently at the University of New South Wales. And he likes to use this test to check the numerical implementation of the models involving consumption decisions, especially working with some of his younger colleagues. Now, other theoretical properties of the solutions that we can derive and prove can be used as the check for the numerical solution of the problem. Right, so we will be talking about consumption savings model again. Here's the Bellman equation that I'm sure everybody can recognize at any time of the day by this time. It is discrete time, infinite horizons, no time indices, you can see. Continuous choice is still C, it's still restricted between 0 and M denoting the current level of wealth or consumable resources in the beginning of the period, and it is discretized. Now, income is stochastic and follows log normal distribution. And again, we're looking at the version with stochastic income rather than stochastic return, so both. Let's look at the first-order conditions. So here's the maximization problem, and we are maximizing it with respect to consumption. I'm going to write the conditions for the interior solutions only. So I'm disregarding the fact that the constraints are imposed on the choice of consumption. Instead of Kuhn-Tucker's conditions, we're just going to equalize to 0 the first derivative and deal with the restrictions separately. Well, you can see straight away that if u of c is log, so it satisfies the another condition, this utility function goes to minus infinity as c approaches 0, with derivative going all the way to plus infinity. Then the lower bound will never, the lower bound on c will never be bounding, right? It's never going to be optimal to put c exactly equal to 0, because then this term becomes minus infinity. It's not the case with the upper bound, and then it does require special attention. But let's look at the interior solutions only for now. So for the interior solution, we can write the first order conditions for this maximization problem, differentiating with respect to C, and I just plugged in C star as the solution that must satisfy this condition. So we have the marginal utility, and then we have this term here, which still has the expectation over the stochastic income. That's okay. We can differentiate inside of the integral, and the expectation is just an integral. Then we have the derivative of the value function evaluated at this at the same point, and then chain rule, we get the -1 out of this C and also the R. So R comes here and -1 is here, and this needs to be equal to 0 for the C star to be a critical point or the optimal point. Now, this equation here implicitly defines a function of C star as a function of M, right? Everything else like beta R, Y, or parameters of the distribution of Y, everything else is fixed. It's only M which is the parameter in this expression here. So we have a function C star of M that the first order conditions define. And that, of course, that is a policy function that tells us what's the optimal choice given the current state in which the dynamic model resides. Now, to implement this, to calculate the optimal the optimal consumption, numerically, we would have to have the derivative of the value function. And if you remember, we are dealing with this expectation and calculation of this whole term by interpolating the value function and then computing the expectation using quadrature or something like that. That means that we are not very well approximating the derivative of the value. And so without special provisions, we could write an alternative numerical procedure where the derivative of the value function is also well approximated. It's not impossible, but without special provisions, the derivative of the value function is not available. So what can we do instead? Imagine that we just write a function of two variables, some function g. This is what I call maximant and that's what's called maximant in the Bellman equation. This is just a function of two variables, m and c, and it's basically everything which is under the maximum operation in Bellman, right? But now let's treat it as a function of two variables. Well, the way we've written it means that that the solution to the Bellman equation, the policy function, or the solution to the problem, right? The argmax in the Bellman equation, the policy function, satisfies this equality. If we plug the C star into the G function, this is going to be a function of M, and that's exactly equal to the value. That's due to the Bellman equation, right? So if we plug back the solution into the Bellman equation, we get the value function. But that means that we can try to differentiate this value function using the total differentiation rule, right, applied to the G function. So we differentiate G with respect to M, and then differentiate G with respect to the second argument, and the chain rule applies here because C is a function of M. And we have this second term. Well, now this first component in the second term, that's exactly zero by the first order condition, right? So it's when consumption is at the optimal level, then this is exactly the first order condition. And so the whole second part vanishes, leaving us with the derivative of G with respect to M, where C star is treated sort of like constant. And what we get, if we just look at this function now, what we get is this expression. The beta R, then the expectation, and then the derivative of the value, but calculated at a different point. Calculated at the point which we call M prime, right? The resources in the next period. Now, the fact that R is outside of the expectation here, and on the previous slide as well, on the previous slide here, the fact that R can be taken outside of the expectation is only due to the fact that we fixed R. If R was also stochastic, then R would have to be inside of the expectation, multiplying the derivative of the value function. So these derivations are not hard to extend to the case where R is stochastic. Okay, let's put everything together. Remember, we had the first order condition. from 2 slides ago. This one, I just moved, that part to the other side. That's written here. Now we have the envelope condition from the previous slide. And of course, here we sort of made a short derivation of what's called the envelope theorem. The envelope theorem tells you how to differentiate the function, which is in turn maximization, the result of a maximization, which the value function is, of course. So here's the derivative of the value function that we derived here. I'll just write it down on this slide. And let's compare these two expressions. You can see that everything on the right-hand side is exactly the same for both of them, which is a nice coincidence. And we can conclude that in the current period, the marginal utility of the optimal level of consumption is exactly equal to the marginal value, to the derivative of the value function, calculated at the amount of resources available for consumption here. And this is the property that holds in the consumption savings problem and in many other problems as well. Okay, so now let's look at the first order condition. And instead of this v prime, we just plug in this function here. We only have to be careful that here the v prime is applied to the next period available resources, m prime, right? So we need to take the c star and calculate the optimal consumption level as a function of the next period available resources, like written here. Because we are applying, this equality in sort of next period, in the next period, when we're plugging this back in. And then I'm going to write c star as a function of m. That is an implicit function of m as defined by the first order condition. So we end up with this expression here, which says that the optimal consumption, the policy function, is characterized by the following equality. The marginal utility of the optimal consumption in the current period is exactly equal beta r than the expectation of the marginal utility of consumption in the next period, taking the current consumption as given. Right? And observe that here on the right-hand side we have this peculiar nesting of the optimal consumption functions. So here the optimal consumption is calculated at the point m prime, the next period resources, which results from the application of the c star, the optimal consumption in the current period. This whole thing is called the Euler equation. And this is essentially a form of first order conditions for the dynamic model, which is expressed fully in the marginal utilities rather than values. You can see there is no derivative of the value function in this expression at all, and the marginal utility is going to be easy to calculate because we know the analytical form of the utility function. So the marginal utility is going to be very easy to calculate. Wonderful. So this solves the problem of having to track and numerically approximate the derivative of the value function in order to work with the first order conditions for these dynamic models. There are more interesting things that result from the Euler equation. For example, we can look at the consumption smoothing, and this is the theoretical property that has that causes the Keynes test. Imagine that we have a deterministic model so that y is fixed. There is no expectation. And then imagine that beta r equals 1. So if we plug these things into the Euler equation, then this is going to be 1. The expectation doesn't exist. And then we are left with marginal utility equals to marginal utility. Well, indeed, what we have then is that the marginal utility of the optimal consumption today at m resources exactly equals to the marginal utility of the optimal consumption tomorrow, where tomorrow results from the optimal consumption today, but it's not that important here. Now, the marginal utilities can be taken away. The function is exactly equal in these points. So that implies that the consumption itself is equalized. So the optimal consumption today equals to the optimal consumption tomorrow, and that is consumption smoothing. So here's the analytical property where consumption is smoothed perfectly, right, under these conditions. And this is essentially the analytical property that must hold if we solve the problem correctly. Now, we're talking about the optimal consumption levels here, so we would be looking at the trajectory of the simulated consumption, so the simulated consumption path from the model. Simulation is trivial because there's nothing random, so it's like a calculated consumption path, but we can always check whether it's flat or not. Over here, it needs to be completely and absolutely flat. So it's presenting a really good test, and actually from experience I can say that because calculating the optimal consumption by applying the consumption functions, this is nested because this value is entering the m prime. Even a tiny error in the consumption function, in the policy function, accumulates as you proceed with the simulation, and it is extremely difficult to achieve perfectly smooth or perfectly flat consumption path from a model solved numerically. We will have the method in a couple of videos, the endogenous grid point method, which is actually capable of producing a completely smooth consumption path. Okay, now more generally, we can use Euler equation to calculate or to measure the accuracy of the numerical solutions. If we think about Euler residuals, which is basically the right-hand side subtracted from the left-hand side of the Euler equation here, we can call this the Euler residual criterion, and this is going to be a criterion of the policy function, of the solution of the model. And imagine that we calculate this variable or this entity on a dense grid with k points. It has to be a really dense grid so that we not only calculate this deviations at the points where we solved the model, but also between those points. So for some, the grid for the accuracy measure should be denser than the grid that the model used for solving. And then we can take the average square deviation to form a criterion, to form this Q that characterizes the accuracy of the solution. And of course, the lower bound for Q is 0, and the bigger it is, the worse the accuracy is. So this is a convenient way to compare different solution methods for the consumption savings problem. Okay, now let's look at time iterations. As I said in video 37, this is an iterative method for solving an infinite horizon dynamic problems with continuous choices. So the idea is is to look at Euler equation and realize that this is a functional equation where the unknown function is the function c of m, right? So with the function c of m, this equation. For different functions c of m that we can plug in here, we can see whether this equation is satisfied or not. So essentially, we could solve this Euler equation as a functional equation in some functional space, and if we find the solution to the equation, that means that we found a consumption function, the policy function, which solves the Bellman equation and solves our model. And then as an additional step, we can find the value function by essentially plugging in the solution policy function into the Bellman equation, dropping the maximum operator and computing the right-hand side. Now, this is not a trivial functional equation. You can see that c of m enters here under the marginal utility and also enters here twice, right? So it's the consumption function that we calculate at the point, which is itself involving calculating the consumption function. So this is sort of like a nested functional equation with nested functions in there. But we can still write down an operator and express the solution to this equation as a fixed point of a particular operator in functional space. And this operator happens to be this Kalman-Refit operator denoted K. This is an operator that takes C as a function of M as input, okay? And then outputs another C of M function, such that for every value of M, the C prime satisfies this condition, or this equation. And similar to the Bellman operator, when we sort of put the input value function in the right-hand side and get the output value function from the left-hand side, here we are inputting the input consumption function inside of the right-hand side, okay, over here. This is C. But then sort of what we get from the left-hand side, C prime also enters into the right-hand side as in the nested way. So C of M prime appears here twice, and C appears once, and this is the input to the operator, where this is the output of the operator given in this indirect way. So this operator is more complicated than the Bellman operator. It's probably harder to conceptualize, but actually calculating of this is not much more difficult. We still will be imposing a grid on M, and we can calculate the C prime by solving, this equation for a given C, for the given C of M function. So we are given the C of M function, we can calculate the right-hand side, the left-hand side, take the difference, and then minimize this difference. So we're solving an equation for each point of M, and this is even an equation in one dimension. But the big question is it a contraction mapping, right? It would be nice if it is, and it is. So Kalman-Refit operator is a contraction mapping, as shown by Lee and Stachursky in 2014. In Journal of Economic Dynamics and Control. They're looking at a more general problem, actually, than the ones that we've been dealing with. So they are specifically looking at the unbounded rewards problem. And they come up with a reasonable metric space as in a particular norm under which this operator becomes is indeed a contraction mapping. And that's great, right? Because that establishes the existence and uniqueness of the solution of the operator. It allows us to apply successive approximations to find that solution. And moreover, this method, which is akin VFI, the successive approximation, is also globally convergent. So in other words, we can start, here's the algorithm. Here's the algorithm for the time iteration solution method. We can discretize the state space, initialize the policy function C0 of M at the state grid, and this can be anything, right? We can initialize algorithm at any point. So, for example, we can initialize it at the function which is identical to 0, or identical to M, or identical to a fraction of M, something like that. And then we keep track of the iterations, and on each iteration we solve the Euler equation on each point of the grid by using the policy function from the previous iteration inside of the right-hand side of the Euler equation. Then solve for the C in the left-hand side, and point by point construct this new approximation of the policy function C of M. And then we just check for convergence, right? So and iterate, okay, over these 3 steps, loop over the 3 steps in pretty much the same way as the value function iteration solver works. Except now we are applying successive approximations solution method to find the fixed point of a different operator, of the Kalman-Refit operator K, instead of the Bellman operator. Now, what can we say about the accuracy and speed of this solver? How does it compare to the VFI value function iterations solver? with explicit maximization, because otherwise we are not comparing, apples to apples. Theoretical complexity and the convergence rates of these two are the same. They are they have the same they have the same speed of convergence, and to calculate to solve the Euler equation essentially takes as much effort as to solve the optimization problem when looking for the fixed point of the Bellman equation. But the thing is now, devil is in the details. Turns out that the policy functions are easier to interpolate. And remember, when solving for the fixed point of the Bellman equation, we have to interpolate the value functions. Policy functions have less curvature, and so the interpolation errors are smaller. And that implies that numerically, the time iterations converge faster because they accumulate less error, and the time iterations produce more accurate solutions in the end. So even though the theoretical properties of the solution methods could be the same, some of them may operate better than others. So we will do the experiments and do some comparisons in the next video. But so far, this is it for this short video on Euler equation and the time iteration solver. I think that there's a lot of practical work ahead of us, and so see you in that next video.